Okay, we are back. So, where were we before the break? Computer vision and computer graphics. Basically, in computer graphics, you start with model, and you generate your scene. In computer vision, you start from the image, you try to come up with a model. So, computer vision, you can consider it as an inverse problem. So, the more direct one is you create your model, you generate the scene, the whole scene. That is more direct approach. The inverse problem is you start from the scene, you try to come up with a model. That's why some of the problems in computer vision are still unsolved. And strong models of the world are required, so you need to have very strong models about the world. And vision implies reasoning about the world. Basically, vision is AI. So you're going to find a lot of maths, as you guys said. For example, you have a geometry, laws of perspective, how to understand a given scene, and all those questions will come to play when you go for computer vision. So, for example, when you take a scene, then as you can see that this, if you take this straight line, they will meet at some point in the infinity, then you can guess that you are far from the given scene, such kind of information. So, one is you need to understand the geometry, laws of perspective, how things appear from different angle, from different distance. Then you also need to have lighting parameters. So you have light source. So you need to have, when you design a computer vision system, you want to have this robust system that works under any kind of lighting condition. Because when you take an image, it takes the value that is reflected from the surface. But depending on the light source, you get different kind of measurement. Yes? But you want to make the system to be robust to any kind of lighting condition, any kind of lighting change. Light source, surface reflectance, and all those things. So math is also needed when you design the algorithm, for example. This is a simple case of image morphing. Image morphing is basically you have two images, you try to combine them and come up with something different. So you start with this girl's image and this guy's image. You warp to a different space, and then you combine it, then you have this guy and girl mixed, but different guy. So such kind of things, for example, now are becoming famous. Like, for example, NVIDIA have new algorithm which generate human faces that you never seen before. Like, it's just it's generated. It's synthetically generated. Those people don't exist. But when you look at them, they are just real. So such kind of things have a lot of applications. In security, for example, you can fool people around and have ID for people who never existed, and yeah, you can do a lot of cool stuff.
Oh, I have IDs for two people, so that matches both people, right? So more for Falco and me, so when we both can use the same ID to do our...
To the same, you can hack the system. And so, let me show you a simple case. What is depicted in this image? Oh yeah, but for computer, if you see the change of intensity, the difference between the neighboring pixel intensity, the change, what you see is such kind of stuff. It's like, if you say, if the neighboring pixel is higher than or lower than, if you just represent the difference, so that's basically the age. How do you identify ages in an image? For example, if this is the age of the previous image, yeah? You can see this age here, yeah? How you come up with a method to, what is the simplest way to do it? To find the age for this image.
Maybe large changes, like
yes, so basically you try to measure the changes. Yes. So basically try to change the change. So what you do is, for example, the simplest one is from the center pixel, you move up I+1, you subtract that one, and I-1 is like to the left and to the right. You try to see the difference between the center pixel to the right, to the left, to the top, and to bottom pixels. Then see the difference. Then that will give you the age information. It's the difference between the center and the neighboring pixel. That will give you age information. So you can do a lot of type of stuff, like for example, you can use Gaussian filter. And yeah, human vision actually is very robust. It can detect edges very fast. And age info is still too low level. So some problems in computer vision, for example. I will show you some vision challenges. So what are the regions in an image? You can see sand, a tree, an ocean, a sky. For computer, it doesn't know which one is which one. So one problem is image segmentation. Image segmentation is basically you try to segment the image into semantically meaningful regions. Okay? That means the segmentation you have here makes sense. The segmentation you have here are continuous. For example, this, you can see this is like cloud or something like that. The clouds are together. So that is called semantic segmentation. The other is, of course, high level, like for example, you want to understand a given image there. You want to understand the crosswalk, the sign, the building, where the car, where the pedestrians are. These are even, and this also needs to work on under any kind of lighting condition from different angle. So this have a lot of application in autonomous driving, for example, nowadays. In autonomous driving, you need to have a way to know if the pedestrian is crossing, or for example, in drones or any kind of technology, something like that, you try to know where the person is, where he is walking, and who is who, and all those things. So, aside, at least there are 8 levels in human vision system. So there are low-level things like edges, corners, and all those things. Then there are high-level tasks like semantic and something that requires knowledge, intelligence. So the vision system is actually connected with the higher part of the intelligence system. So it's not only low-level. Low-level things are important, but there are different levels of abstraction you need to do. So of course, let's see now. If you look at this lecture today, we started from image acquisition, yeah? We started from image acquisition, and we tried to formulate different problems from computer vision. Now, let's go back to the other side, the computer graphics side. Of course, graphics have a lot of applications. You can do Boeing simulation, for example. If you guys heard, like, the accident that happened, Boeing Max. Yeah, so it's like training and simulators stuff, yeah. And you can do a lot of entertainment, computer-aided design, education, e-commerce, graphics. You guys know it, you love it. That's why you are taking this course. And there is tons of application for it. But in computer graphics, what you start with is always in a model. So maybe your first lab is to create a vertex and to plot a first triangle. Yeah? So you start with a triangle. So earlier we started with the image. But here in computer graphics, you start with the model itself. So any kind of thing can be described by a bunch of triangles. Yeah? So you have this wireframe of a given model, like for example, a 3D model. So you have this X, Y, Z vertices. So for example, you could design any kind of car or any kind of components of the system, or any kind of scene for that matter. Then you have this coordinate system. Then you augment this thing with texture, color. For example, you put texture on that surface, then you have this realistic looking person or something like that. So now we are trying to reconstruct the whole thing from starting from primitive models like triangles you're trying to build. Then you try to render. Given a model, a source of light, point of view, how to render it on screen. Yeah? So that's what you try to estimate when you try to use OpenGL and other tools. So there are different ways of rendering. So what is the difference between global illumination and the direct illumination?
Well, global illumination doesn't really have a point. It's just everything's been illuminated.
Okay. The direct?
Direct illumination, the light origins has an origin in the point and then goes from there. So objects that are obscured by other objects don't get there.
Yeah. So basically when you do direct illumination, for example, when I'm standing here, I have some reflectance. My reflectance influence on other object is not represented. Yeah? On direct, there is nothing, there is no object-to-object light transmission. Like there is a light source, it strikes that surface of it illuminates the surface that you are interested, then that point will be registered. There is no interaction between the objects you have in the scene, which is not realistic, yeah? Which is not realistic. So that's what you do in OpenGL and other libraries. You have this direct estimation. But in global illumination, you consider everything. For example, you have this light source which is very shiny, and that light, when it strikes here, there is some reflectance here. It also shines in addition to that one, in addition to the sunlight source. So the light source could be from different light sources, from reflectance of properties from other surfaces. So you have more realistic looking render. So that is basically, you try to add the light source. In computer vision, you try to estimate the light source. In computer graphics, you try to add the light source. Then you have different kind of light sources. So you have diffuse reflectance. So it's like this part of the course is almost, the lecture is almost a review for you guys. So what is the diffuse reflectance?
Exam question, guys.
According to what it says on the slide right in front of me,
yes,
light hits the surface and is scattered in every direction.
Yeah. So that means it is equally illuminated in every angle. So there is no dominant line of source. The next one I will not show you. Then, what is a specular reflection? Yeah.
Well, light hits an object and is then reflected at an angle, so you can only see the you can see it on the plastic top of that thing. It's like if light shines in from a specific angle, you can see very bright patches if you are in the right place, because the light hits it and bounces off in that direction.
It gets sort of shine.
It has, you can only see it from a different specific direction. It's like
okay, good point. There are a lot of good points. We need to summarize this. Summarize.
surface reflects more in one direction than in others?
Yes, so that's the main idea. So you have very strongest mirror of angle. At some angle, you have the strongest response. In diffuse reflectance, you have equal in every angle. Then now where we are going with this informed model, for example, when you add all this reflectance, you are trying to add diffuse reflection and ambient. What is the ambient one?
It's like a constant.
Yes, so that is a constant across the whole scene is illuminated by some constant values. That is the ambient. So basically, in Fong's model, you are creating the light model. In computer vision, you don't have the light model. You try to estimate the light model. You try to estimate the reflectance. You try to estimate the illuminant. In computer vision, you invent. In computer graphics, you invent your light source. You invent where the light source should be. You invent everything for yourself. You design. You start from a model. So, for example, in ray tracing, you have very cool-looking render. Yeah. Then, if you want to do something animation, for example, you try to define a given object. That object have a mass, velocity, acceleration, color, lifetime, all those things. If you want to animate it, for example, if you want to animate two balls hitting each other, you can model this using computer graphics, how the motion will be after the collision, and all those things. For example, you can write a code for collision detection, and all those things. Yeah. In computer vision, you try to estimate like how fast a person is going from the video. So, for example, one of the application of computer vision is human tracking, pedestrian tracking. You try to track the person as it goes through some scene, and how many people are going this direction or this direction. All those things are like, it's almost complementary problems you have in computer vision, you have in computer graphics. Then, for example, in particle system, if you want to render, so what you try to do is you try to create new particles, then delete any expired particles, then update particles based on some attributes, motions, and something like that. Then repeat this thing for the whole for time you need to simulate. So as you can see, the problems, what I want to emphasize here is most of the problems you have in computer vision are the mirror image in computer graphics. So my next question is, you guys seen computer vision and computer graphics, how it's related? How can you use it in your computer graphics project? So this is the last question I'm going to ask.
Make a bot would be fun.
Yeah.
Like have like read the screen pixels.
Okay.
Then try and see if it could play the game or something.
Bot.
A bot, like
a bot. Okay. Yeah.
So you read the color on the screen.
Yeah.
And then based on like where the Pac-Man or whatever game
yes.
is, then you can try it.
Yeah. Okay, that's one application.
Take an image of a room and then construct a 3D model of it based on the image?
Yeah. You can do the model and everything. How you can use it in your project? For example, you are probably working on 3D Pac-Man or.
Oh, you mean in this? Oh, what
yeah.
You mean, like, okay. How to implement anything else except what he says for 3D Pac-Man, to be honest.
Yes, I'm just trying to push this idea in case you guys are, how you can use computer vision to make your Pac-Man even super cool. Pac-Man ++.
So what is when you develop your games, right? So what are your figures also, what they're generally doing? if you, I don't want to use that term. When you do something with Pac-Man, right? So, are they actually actively, are you actively interacting with them? Pac-Man, for example. Now, I'll probably put it back to Ahmed's perspective and say, think about what you're doing in graphics. What would be the opposite? How can computer vision help perhaps interact with the player character, with Pac-Man? Could you see a way that you can use computer vision for that purpose?
AI?
Yeah, but you're just throwing AI in there. AI is in there, of course. But more specifically, what kind of could be done with the AI? What specifically could be done there?
Well, then AI can actually see the player instead of just having a radius around them.
So who's the player?
The player character, Pac-Man.
Okay.
For example.
Yeah, okay.
Well, I suppose you could use it for testing. I suppose also, like, if you have like trying to see if it's a computer vision, you could make some sort of weird testing model, like trying to if it could use automate gameplay, like see if the vision wasn't able to detect something, then yeah, just like. That's really a bit far out there. It's possible.
But that sounds interesting. I mean, we could do de facto do a functional testing framework, right?
Yeah,
without building any sort of
thing.
structural assumption into the environment. Yes. So that is pretty cool.
I mean,
+1 for that one. You can do that for your project.
I mean, using computer vision in order to do testing is kind of like throwing dynamite in a laser vision. It's
you could probably like play for a level extremely fast and everything. Just speed it up or something.
Well, the point is the advantage of using computer vision means you may not, in cases you don't have access to the code base, you can still do testing.
that is true.
Right? So, because we don't need to make structural assumptions.
Yeah.
But what other aspects? Because it is onto something
Yeah.
here.
You can draw that on the paper and then.
Okay.
Cool.
Yeah.
That is seriously cool.
Yeah. You can make dynamic map. For example, I want to play in this scene. Then you just show it the computer. Then the computer takes that and make it. That's interesting.
That's cool.
Yeah, that's really interesting.
Nice.
Just use white paper and like detect the lines and yeah, that's really cool.
Are you mobile by any chance?
Yes.
So, what about a mobile project on that one? With Ahmed as supervisor. Perfect. Think about it anyway.
Yeah, that's really cool.
So that would be interesting, seriously.
Yeah. Like for example, can you use for interaction with because with the Pac-Man they always use these arrows, which is not natural. With keyboard it's like boring. What if you use webcam to guide the Pac-Man, like, you know?
Oh, yeah, you think about it.
Yeah, you can use gesture. You can use gesture, like gesture recognition for moving the Pac-Man, and you can just play around, you know? So it will be more even fun and more exercise than sitting on keyboard and left, right, and left, up. So, yes, yeah, sorry.
But also thinking wider, right? So this sounds like a fun activity and just playing around with tech, but think about accessibility, right? So you may have players that simply can't use, for whatever reasons, their cursor keys, right? Why shouldn't they be able to play Pac-Man as well? Perhaps you can use your eyes to point in different directions and therefore control the image, right? So there's a lot of opportunity there to actually engage people that would otherwise not be able to. So.
Yes, yeah. You can make your product be acceptable by large margin of the people. I think you can do a lot of even
You
more.
will improve with sound as well, like right, forward,
Yeah. Sound is
That's
also
not
one
really
option.
vision, but, yeah.
No. Actually, the methods, especially after the start of this deep learning, I don't know if you guys heard about deep learning neural net stuff?
Not like I read a lot about it. Not,
Yes,
not at school.
Okay, no, yeah. Then it's like most of the things are combining. It's like the technology, the core technology is becoming the same. Everything in backbone is neural nets. So you can literally do that. For example, Google captioning, in which, for example, you just put an image on the net, and the Google, when you search it, it will automatically recognize the scene and something like that, and it will give you like outdoors pictures.
Tags.
Without even tag, it will generate the tag for you.
Yeah.
So it's basically understanding the content of the image and trying to generate text. So there is a lot of cool things you can do. So with that, I will finish my presentation. And in case you guys are interested in computer vision course, there is a course that's going to be running next semester, which is IMT2531 computer vision course. So with that, I will finish my presentation, and if you have questions, I will be very happy to answer.
How did you like get involved making like medical applications for computer vision? Is that like Anthony collaborates
Yes.
with the hospital or anything?
Yes, I'm working with the